Hi, I am Sanjay Patel. In this video, I am going to solve some interesting problems based on beta and gamma functions. Before that, let us recall the definitions of beta and gamma functions and some few properties what we already proved in our earlier videos. So first definition of a gamma function. So we know that gamma function is defined like this. This is equal to integral 0 to infinity x raised to n minus 1 into e raised to minus x dx. Our definition of beta function, beta m comma n, let me call this way, this is 1, 2, beta m comma n is equal to integral 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1 dx. Then we know that gamma n plus 1 is equal to n into gamma n. And further, if n is a natural number, then gamma n is n minus 1 factorial. This is true for every real number n greater than 0, and this is for every n belongs to n. Then we have another very useful result about gamma function is gamma n can be expressed as 2 times integral 0 to infinity x raised to 2n minus 1 into e raised to minus x square dx. So these are the few results about gamma functions. We also have some more results. Let me write few results about beta function as well. We know that beta m comma n can write as say 2 times integral 0 to pi by 2 cos raised to 2m minus 1 theta into sin raised to 2n minus 1 theta d theta. Another similar result which is very useful, we can write this as integral 0 to pi by 2 say sin raised to p theta into cos raised to q theta is equal to 1 by 2 times beta of p plus 1 by 2 q plus 1 by 2. Then the next thing is the relation between beta and gamma function, that is beta of m comma n is equal to gamma m comma n upon gamma of m plus n. Another useful result is duplication formula that says gamma of 2n is equal to 2 raised to 2n minus 1 upon root pi into gamma n plus 1 by 2. Okay. And finally, I want to just mention the two important values, that gamma 1 is 1 and gamma of 1 by 2 is square root of pi. So keeping in mind all these results which are going to use for solving problems of beta and gamma functions. So let us start with the first problem. Let me remove this. Okay. Fine. So for now I am going to solve problems of beta and gamma function. The first one, prove that integral 0 to infinity x raised to 4 upon 1 plus x raised to 15 dx is equal to 1 upon 10010. Okay. So first of all, what I will try to do is I will convert this integral in some known expressions of beta or gamma function. In this kind of integral, it is when there is 1 plus something, it is easy to take a substitution like x equal to say tan square theta or something like that. But if it is 1 minus x squares, then you should take x equal to sine theta or cos theta to convert everything into sine and cos. This is only some idea, not necessarily always true. So let me take a substitution here. The x is equal to tan square theta. Okay. So this implies if you find derivative dx is 2 tan theta, derivative of tan square theta is 2 tan theta, and derivative of tan theta is sec square theta d theta. And you know, whenever we take a substitution in definite integral, you must change the limits of integration also. So we can write when that x is equal to 0, that is tan theta is 0, we have theta is equal to 0. And when x is equal to infinity, that is tan square theta is infinity, that gives us theta is equal to pi by 2 because tan pi by 2 is infinity. So putting all these values in this integral, what we'll get is integral 0 to infinity x is to 4 upon 1 plus x raised to 15 dx. This becomes integral when x equal to 0, we have theta is equal to 0. So we write 0 here. When x equal to infinity, theta is equal to pi by 2. So I will write pi by 2 here. And x raised to 4. So we have tan raised to tan square theta, x is tan square theta raised to 4 upon 1 plus tan square theta raised to 15 into dx is 2 tan theta into sec square theta d theta. Okay. Let us simplify this. So this is equal to integral 0 to pi by 2. This is tan raised to 8 theta, and 1 plus tan square is sec square theta, and raised to 15 is there, so it is sec raised to 30 theta. And here we have 2 tan theta into sec square theta into d theta. So what I will get is 2 times integral 0 to pi by 2. Okay, this 2 I am taking here outside of the integral sign. Then tan raised to 9 theta, and this upon sec raised to 32. Or I can write sec raised to 28 theta. This one sec square will be cancelled into d theta. And tan theta is sine theta upon cos theta. So this we can simplify further and express in sine and cos. So tan theta is sine theta upon cos theta. So this is sine raised to 9 theta upon cos raised to 9 theta. So let me write this way. Sine raised to 9 theta upon cos raised to 9 theta. And that 1 upon sec raised to 28 is cos raised to 28 theta d theta. So this is equal to 2 times integral 0 to pi by 2 sine raised to 9 theta and cos raised to say 28 minus 9, that is 19 theta d theta. Okay, and we know the formula for this in terms of beta function for this integral. So this I can write as 2 into, just I'm using the formula, say 1 by 2 times beta of 9 plus 1 by 2 comma 19 plus 1 by 2. Okay, you know this formula, integral 0 to pi by 2 sin raised to p theta into cos raised to q theta d theta, that is 1 by 2 times beta of p plus 1 comma q plus 1 by 2. Now onwards I will not write all such formulas here, I will write the value directly. So this is equal to beta of 9 plus 1 is 10 by 2, that is 5, and 19 plus 1, that is 20 by 2, that is 10. And this is equal to, since 5 and 10 are integers, let me write one more step. This is gamma 5, gamma 10 upon gamma 5 plus 10, using the relation between beta and gamma function. You know beta mn is equal to gamma n upon gamma of m plus n. So this is 4 factorial, this is 9 factorial, and this is 14 factorial. Okay, because 15, now 15 is 14 factorial. And if you simplify this, you will get the required answer, which I am writing directly, 1 upon 10010. That's all. Let us solve the next problem, number 2. Prove that integral 0 to 1 x square upon 1 plus x square raised to 3 dx is equal to pi upon 32. Okay. So let us start with the given integral. What I am going to do here is I want to convert this again into sine and cos. So it is better to take only x equal to tan theta. So 1 plus tan square theta becomes sec square theta. And then we can simplify very easily. So that's an easy idea. So let us take x is equal to tan theta. This implies dx is equal to sec square theta d theta. Okay, and also when x is equal to 0, that is tan theta is 0, from this relation, when x equal to 0, so tan theta is 0 implies theta must be 0. And also when x is equal to 1, that is tan theta is 1, and therefore theta is pi by 4. Okay, putting all these values in that this given integral, I can write integral 0 to 1 x square upon 1 plus x square cube dx is equal to integral 0 to pi by 4. Now x is tan theta, so x square is x is tan theta, so x square is tan square theta, and denominator 1 plus x square, that is 1 plus tan square theta is sec square theta, and whole raised to 3 is there. Dx we already obtained, that is sec square theta into d theta. Let us simplify this. So this is equal to integral 0 to pi by 4 tan square theta upon, this is sec raised to 6 and minus 2, so it is sec raised to 4 theta d theta. This is equal to integral 0 to pi by 4 tan square theta is sin square theta upon cos square theta, and this is cos raised to 4. So finally, if you simplify, it is easy to see this is sin square, and 1 upon cos square will be cancelled with this, and what we will get is sec square theta, that gives you cos square theta d theta. Okay, and this I can convert into sine 2 theta. If I multiply and divide by 4, so I can write like this: 1 by 4, 0 to pi by 4, 4 sine square theta cos square theta d theta. Okay, and this is nothing but sine 2 theta square, because this 4 sine square theta cos square theta you can write as 2 sine theta cos theta whole square, like this: 2 sine theta cos theta, 2 sine theta into cos theta whole square d theta. So this is equal to 1 by 4 times integral 0 to pi by 4 sine 2 theta, so that is sine square 2 theta d theta. Now in this integral I would like to take a substitution, because I don't have any formula for 0 to pi by 4. So if I put 2 theta is equal to say something say t, then I may get pi by 2 here. So let us, that idea tells us to take a substitution. T is equal to 2 theta, and therefore dt is equal to 2 into d theta. So d theta is 1 by 2 times dt. Now also when say theta is equal to 0, the value of t is 0, and when theta is equal to pi by 4, theta is equal to pi by 4, we have t is equal to pi by 2. Putting all these values in the above integral, I can write this integral 1 by 4 times 0 to pi by 4 as 1 by 4 integral 0 to pi by 2 and sine square t, and d theta is 1 by 2 times dt from this. Okay, so this gives us 1 upon 4, rather 1 upon 8. I can take that constant here, say 1 upon 8 times integral 0 to pi by 2 sine square t dt. And now for finding the value of this integral, you can use the reduction formula also, but if you want to try beta gamma function, you can write or you can use this formula, and that is we have integral 0 to pi by 2 sine raised to p theta into cos raised to q theta d theta is equal to 1 by 2 times beta of p plus 1 by 2 and q plus 1 by 2. So comparing with this, you can note that the value of p we can take here we can take p is equal to 2 and q is equal to 0. And applying this formula, we can write the above integral as, so the above integral is equal to 1 upon 8 into 1 by 2 times beta of p is equal to 2, so 2 plus 1 by 2, and q is equal to 0, so 0 plus 1 by 2. Simplifying this, what I will get is 1 upon 16 beta of 3 by 2 and 1 by 2. Now we are not getting integer here, so it is an interesting thing. To find the value of this beta function, let us use the relation between beta and gamma function. Beta m comma n is gamma m into gamma n upon gamma of m plus n. So you will get this thing. Okay, so I am using that relation between beta and gamma function. Beta mn is equal to gamma m, gamma n upon gamma m plus n. Okay, so we are using this. This is equal to 1 by 16 gamma root 3 by 2. Okay, that you can think as gamma of say 1 by 2 plus 1, because 3 by 2 is 1 by 2, and this is gamma 1 by 2 whose value is root pi. So this gamma 1 by 2 I am writing as root pi, and this 3 by 2 I am expressing as 1 by 2 plus 1. And this is 3 plus 1 by 2, that is 4 by 2, so it is gamma 2. Now we can find all these values very easily. For the first gamma, this gamma value, I can write gamma of n plus 1 as n gamma n. So it is 1 by 2 gamma 1 by 2 into root pi, and this gamma 2 is 1 factorial because 2 is integer. So I am using this result, gamma n plus 1 is equal to n into gamma n. So that is the important thing here. And again, gamma 1 by 2 is root pi. So this gives me 1 upon 32 into root pi, okay, upon 1. This 1 by 2 goes down. So final answer is pi by 32, okay, which is the required value. Let us go to the next problem. So the next problem is this. Prove that integral 0 to pi by 2 sine raised to p x dx into, means this multiplied by integral 0 to pi by 2 sine raised to p plus 1x dx is equal to pi upon 2 times p plus 1. So let us prove this. It is very, very simple. So I start with the LHS, that is integral 0 to pi by 2 sine raised to px dx into integral 0 to pi by 2 sine raised to p plus 1 x dx. And I am going to use that formula for beta function. You know, integral sine raised to p into cos raised to q 0 to pi by 2 is 1 by 2 times beta of p plus 1 by 2 comma q plus 1 by 2. Here q is not there. So this I can write as 1 by 2, this right here. We know that integral 0 to pi by 2 sine raised to p theta into cos raised to q theta. As I told you, this is very, very useful formula. You will need it in many, many examples. Okay, so we can write the above integral as this is equal to 1 by 2 times beta of p plus 1 by 2 comma 0 plus 1 by 2. Here q is not present, into 1 by 2 beta of p plus 1 plus 1. So it is p plus 2 by 2 comma 0 plus 1 by 2. So here in this integral p is p plus 1. So putting p equal to p plus 1, we get p plus 2 by 2, and cos term is not present, so we take q is equal to 0. Let us simplify this. This is equal to 1 by 2 times beta of p plus 1 by 2. Let me write here, this is 1 by 4, because 1 by 2 into 1 by 2 is 1 by 4, gamma 1 by 2 into beta of p plus 2 by 2 comma 1 by 2. This can be written as 1 by 4 using the relation between beta and gamma function, gamma m, gamma n upon gamma of p plus 1 by 2 plus 1 by 2 into gamma of p plus 2 by 2 into gamma of 1 by 2 upon gamma of p plus 2 by 2 plus 1 by 2. So let us simplify this, and what we can do here is this term is p plus 2 by 2, so I can cancel this value with this thing, because both are same terms. P plus, if you simplify it, is p plus 2 by 2, so this will be cancelled. What is left is only these terms, so I can write it as, say, 1 by 4 times, say, what is this, gamma p plus 1 by 2 into gamma 1 by 2 into gamma 1 by 2 again. Okay, so gamma 1 by 2 upon this gamma of p plus 2 plus 1, so it is gamma of p plus 3 by 2. Okay, this we can express in the denominator we can express in a different way. The 1 by 4 gamma p plus 1 by 2, this is gamma of 1 by 2 square upon this I can write as p plus 2 rather p plus 1 by 2 rather. Yes, let me write that 3 as 1 plus 2, so it is p plus 1 by 2 plus 1. Is it fine? And this p plus 3 we can write as p plus 1 plus 2, and then separating the denominator we can write p plus 1 by 2 plus 1. So it is 1 by 4 gamma of p plus 1 by 2 gamma square upon, here I can use the result gamma n plus 1 is equal to n gamma n. So p plus 1 by 2 into gamma of p plus 1 by 2. So again these two will be cancelled. Okay, so what is left is gamma 1 by 2 square, and that gives us pi, and this 2 will be cancelled with this will be cancelled with this, and we'll get 2 here. So final answer is 1 upon 2 into p plus 1, and this is nothing but root pi square. So answer is pi upon 2 times p plus 1. Okay, now let us go to the next problem. I think this is the third problem. So next, problem number 4. Prove that integral 0 to infinity e raised to minus x raised to 4 dx is equal to 1 by 4 into gamma 1 by 4. So in the left hand side integral, I want to take some substitution to have some known formula. If I take say x raised to 4 is equal to t, what I will get is dt is equal to 4 into x cube dx. And not only that, when x equal to 0, we have t is equal to 0, and when x is equal to infinity, we have t is equal to infinity. So therefore the given integral, that is 0 to infinity e raised to minus x raised to 4 into dx. I can write as integral 0 to infinity e raised to minus t, because x raised to 4 is t, x raised to 4 is t, and this dt, from this I can write dt upon x cube. So what is x? Let me write this way. From this I can write x is equal to t raised to 1 by 4. That I can substitute here. So what I will get is dx by putting x raised to 1 by x is equal to t raised to 1 by 4 in this. I will get 1 by 4 times this is t raised to 3 by 4. When you go, it will go in the denominator. It is t raised to minus 3 by 4 dt. Correct? Just put x is equal to this value and then simplify and make dx as a substitute to the formula. You will get 1 by 4 times this. So this into 1 by 4 t raised to minus 3 by 4 into dt. Now this is something familiar, and it is similar to that gamma function if you write properly. So 1 by 4 times integral 0 to infinity t raised to minus 3 by 4. I can write t raised to minus 3 by 4 as, just a minute, I can write as say 1 by 4 minus 1. Yes, 1 by 4 minus 1, like this. This is minus 3 by 4 into e raised to minus t dt. And this is nothing but gamma of 1 by 4 by definition of gamma function. So this is gamma of 1 by 4. So the result is proved. Okay. Next, let us go to the problem number say 5. Prove that integral 0 to 1 upon or dx upon square root of 1 minus x raised to n. This is equal to root pi upon n into gamma of 1 upon n upon gamma of 1 upon n plus 1 by 2. Here, to convert this into known beta or gamma function, let us remove the square root here by taking, or no need to remove the square root, we can write directly also. Say, let me take 1 minus x raised to n as t. Okay, so that gives me x raised to n is equal to 1 minus t. Okay, and therefore from this I can find x as 1 minus t raised to 1 upon n, taking nth root both the sides. And therefore if you find dx, this is to be replaced, so it is 1 upon n, derivative of this thing, 1 minus t raised to 1 upon n, derivative is 1 upon n into 1 minus t raised to 1 upon n minus 1 into derivative of 1 minus t is minus 1 into dt. Okay, and also think of the limits here. When x is equal to 0, t is equal to 0, and when x is equal to 1, when x equal to 0, if you put x equal to 0 here, you will get t equal to 1, and when x equal to 1, we will get t equal to 0. It is the reverse thing. So this integral now we can express as integral 0 to 1 upon square root of 1 minus x raised to n dx. We can write as integral For x equal to 0, we have t is equal to 1. And when x is equal to 1, we have t equal to 0. It is like that. And 1 upon 1 minus x we have taken as t. So it is t raised to 1 by 2 into the dx. dx is this. So it is minus 1 upon n into 1 minus t raised to 1 upon n minus 1 into dt. Now, if you remove this negative sign, then you can interchange this limits of integration. As you know, integral a to b is same as minus integral b to a. So this is integral 0 to 1. This is equal to integral 0 to 1. 1 upon n I can write outside, which is a constant. This is t raised to minus 1 by 2 into 1 minus t raised to 1 upon n minus 1 into dt. This can be written as 1 upon n integral 0 to 1, integral 0 to 1, minus 1 by 2 I can express as 1 by 2 minus 1. This is t raised to 1 by 2 minus 1, because we know such expression is there in the beta function. So this is actually the expression for beta function. So I can write this as 1 upon n into beta. You know, beta m comma n is equal to integral 0 to 1 x is to m minus 1 into 1 minus x is to n minus 1. Your m and n are say 1 by 2 and 1 by n. Okay, by definition of beta function. Okay, so now we can find the value of this beta function very easily using the relation between beta and gamma function. So this is equal to 1 upon n into gamma 1 by 2 gamma 1 upon n upon gamma of 1 by 2 plus 1 upon n. Okay, so fine. And this gives me the value of gamma 1 by 2 is root pi upon say n, this gamma 1 upon n as it is, and this is gamma of 1 upon n plus 1 by 2. I think this is the required answer. Let us check. Yes, root pi upon n, gamma 1 upon n divided by gamma 1 upon n plus 1 by 2. So it is done. Okay. Let us take the next problem, number 6. Say, prove that beta m comma m into beta of m plus 1 by 2 comma m plus 1 by 2, okay, is equal to pi upon m into 2 raised to 1 minus 4m. 2 raised to 1 minus 4m. So it is just a matter of simplification. We'll start with the left hand side. Here, beta of m comma m into beta of m plus 1 by 2 comma m plus 1 by 2. We can use the relation between beta and gamma function and write it as gamma m upon gamma m plus m, that is gamma 2m, into gamma of m plus 1 by 2 gamma of m plus 1 by 2 upon gamma of m plus 1 by 2 plus m plus 1 by 2. So it is gamma of 2m plus 1. Okay, sum of these two is 2m plus 1. Okay, this we can write as gamma m square. Let me first check this. this is gamma of m square into gamma of m plus 1 by 2 square upon gamma 2m plus 1 we can express as 2m into gamma 2m by the formula gamma n plus 1 is equal to n gamma n. So what I will get is 2m into 2m gamma 2m, because gamma n plus 1 is equal to n into gamma n. Okay. Now what we are getting here is this is equal to say 1 upon 2m into gamma m into gamma m plus 1 by 2 square upon gamma of 2m square. Let me call this as result star. And we have something like this in a very popular formula, which is the duplication formula. So we know that duplication formula is gamma 2m is equal to 2 raised to 2m minus 1 upon square root of pi into gamma m plus 1 by 2. This is from duplication formula. So this value, this expression, rational expression, I can write, not rational, it's an expression we can write as say 2m, or let me write the other way, taking the cross multiplication here. From this we get say gamma m into gamma m plus 1 by 2 upon gamma 2m is equal to root pi upon 2 raised to 2m minus 1. Okay, and if we square both the sides, what we'll get is gamma m into gamma m plus 1 by 2 upon gamma 2m whole square is equal to pi upon 2 raised to square of this is 4m minus 2. Okay, so this is the derivation from this duplication formula. This double star now I want to substitute in place of this expression. So what I will get is the value of left hand side. This is my LHS. Okay, this is LHS, which is written here 1 upon 2m times this. So I can write from star LHS is equal to 1 upon what was that? 1 upon 2m, yes, 1 upon 2m into pi upon 2 raised to 4m minus 2. So this I can write as pi upon m. This m and pi I am writing separately. This is 2 raised to 1. So we'll get 1 upon 2 raised to 4m minus 1. And according to the required result, I can write it as this is equal to 2 raised to 1 minus 4m, which is nothing but our right hand side. So the result is proved here. So this way you can solve problems of beta and gamma functions. In the next lecture, we'll take some more interesting problems based on this beta and gamma function. So just keep preparing all the different results or properties of beta and gamma function so that you can solve such problems very easily. So thank you.